Let's be honest, when we picture humanity's end, our minds usually jump to something dramatic, right? A colossal asteroid hurtling through space, a supervolcano erupting in a fiery cataclysm, or maybe even a rogue black hole. But what if the real threat isn't some sudden, explosive event? What if it's something far more insidious, a quiet, inescapable fate woven into the very fabric of our planet's atmosphere? Scientists have actually uncovered a ticking time bomb, and it's not about some distant cosmic collision. It's about the air we breathe, the very thing sustaining us, turning against us. Long before our sun swells to swallow the Earth, the atmosphere will betray us, leading to a silent, global suffocation. And here's the kicker, the countdown has already begun. Take a deep breath. Really feel it. That cool, life-giving rush. About 21% of the gas filling your lungs right now is free deoxygen, or O2. This isn't just any gas. It's the crucial molecule that complex animals like us, and everything from tiny insects to massive whales, reliably burn for energy. It's our metabolic fuel. Where does it come from? Mostly from plants, quietly churning it out every daylight hour, a process they've perfected over the last 450 million years. We tend to treat this 21% oxygen as a cosmic birthright, an endless supply. But here's the uncomfortable truth. It's actually a temporary loan. And new supercomputer models, published in Nature Geoscience, suggest that loan gets called in a lot sooner than you might think, roughly 1 billion years from now. Not 5 billion, the lifespan of our sun, but 1. At that point, atmospheric oxygen levels are predicted to plummet to less than 1%. To put that into perspective, imagine a mountain climber today at the summit of Mount Everest, where oxygen is already scarce. They'd black out in seconds. For everything larger than a microbe, Earth will become one giant, inescapable death zone. There won't be any Hollywood drama, no fire in the sky, just a slow, irreversible fade to breathlessness. The planet will revert to an atmosphere similar to what it had before the Great Oxidation Event, over 2 billion years ago, when only microbial life existed. It's a sobering thought. The very air that makes our world so vibrant is poised to vanish, not in a cataclysm, but in a drawn-out, silent collapse. So, what's behind this impending atmospheric collapse? Ironically, it's the very star that gives us life, the sun itself. Our sun, a seemingly stable yellow dwarf, is actually still evolving. It's only middle-aged, and like any aging star, it's getting brighter. Every 110 million years, the sun burns approximately 1% brighter. This might sound like a small change, but over geological timescales, it adds up to a fundamental alteration of Earth's climate and atmospheric chemistry. That extra energy warms Earth's surface, and what happens when things get warmer? More water evaporates. This increased evaporation puts more water vapor, a very potent greenhouse gas, into the atmosphere, amplifying the warming effect. It's a vicious cycle. But there's another critical factor: warmer oceans. They dissolve less carbon dioxide. Think about it. A cold soda holds its fizz better than a warm one, right? The same principle applies to CO2 in the ocean. This reduced oceanic absorption throws a wrench into Earth's long-standing climate thermostat, the carbonate-silicate cycle. This cycle, which acts as a geological regulator, normally balances atmospheric CO2 by locking it into rocks and releasing it through volcanic activity. But as the planet heats up, this delicate balance wobbles. In essence, the sun cranks up the heat, the oceans release steam, and CO2, the essential raw material for plant photosynthesis, becomes increasingly scarce. Plants starve first, and then, inevitably, oxygen production starves second. It's a slow, inexorable squeeze on the very foundations of our biosphere. Now, let's fast forward about 600 million years. The sun's luminosity will be significantly higher, and its impact on Earth's climate will be profound. At this point, carbon dioxide concentrations in our atmosphere are projected to slide below a critical threshold, 150 parts per million. This number isn't arbitrary, it's a death knell for a vast majority of plant life. But because most trees, wheat, and the crop plants we rely on today use a biochemical pathway called C3 photosynthesis. This pathway, while efficient in today's CO2-rich world, simply can't function below that 150 parts per million mark. The consequences will be catastrophic. Forests, those majestic green lungs of our planet, will vanish continent-wide. Imagine entire landscapes, once teeming with life, becoming barren. They'll be replaced by more resilient, scrubby grasses that employ a different, more CO2-efficient strategy, C4 photosynthesis. C4 plants are like the metabolic innovators, capable of squeezing carbon dioxide more effectively from a leaner atmosphere. While C4 plants can still photosynthesize and produce some oxygen, the sheer scale of the ecological transformation will be immense. Biodiversity will collapse dramatically as ecosystems unravel. Many species will simply run out of food and suitable habitats. Oxygen will keep trickling out for a time, thanks to these hardy grasses, but the trend is undeniably set. Less green, less diverse life means less O2 in the long run. The atmosphere will be wobbling on a knife edge, its stability compromised, just waiting for the next, inevitable push. Let's jump ahead to the billion-year mark. The sun's luminosity is now a full 10% higher than it is today. Average surface temperatures will hover around a scorching 46 degrees Celsius or 115 degrees Fahrenheit, making much of the planet unbearable. At these temperatures, a new, terrifying phenomenon kicks in, the moist greenhouse effect. It's not just that the oceans get warmer, they begin to evaporate in earnest, releasing vast quantities of water vapor directly into the atmosphere. This water vapor, a powerful greenhouse gas, traps even more heat, creating a runaway feedback loop. Critically, this isn't just about surface heat. The rising temperatures push water vapor higher and higher, flooding the stratosphere. High above the protective ozone layer, where the air is thin and UV radiation is intense, those H2O molecules are ripped apart by the sun's powerful ultraviolet light. The lighter hydrogen atoms escape into the vacuum of space, while the oxygen sticks around, but only briefly. What little carbon dioxide remains is then captured by weathering rocks, a process that usually helps regulate climate but now becomes a carbon sink, further depleting the atmosphere. And here's another devastating blow. Without active plate tectonics, which is slowing as Earth's interior cools, volcanic CO2 no longer replenishes the atmosphere. Plate tectonics typically acts as a global conveyor belt for carbon, releasing it through volcanoes and burying it through subduction. With this cycle grinding to a halt, plants lose both their vital carbon source and their stable climate. Global photosynthesis crashes. In less than 10,000 years, a mere geological blink of an eye, oxygen production falls to 1% of current rates. Atmospheric O2 plummets to concentrations last seen 2 billion years ago, back when Earth was a microbial-only planet. Complex life, everything from ants to whales, every flower, every fungus, quietly asphyxiates. It's the end of an era for macroscopic life. After complex life dies out, Earth just keeps baking. Over the next 200 million years, temperatures soar well past the boiling point of water. Imagine a world where the very air is scalding, where rain turns to steam before it even hits the parched ground. The last hypersaline seas, what little water remains, retreat underground or to the poles, becoming isolated, toxic puddles. But even in this hellish landscape, life, in its most tenacious forms, persists. Only extremophile microbes, anaerobic bacteria, archaea that can eat rock and excrete sulfur, will survive in those shrinking, super-harsh pockets. These are the ultimate survivors, adapted to conditions that would instantly kill anything else. Oxygen, by this point, is a mere trace gas, a rounding error in an atmosphere now dominated by nitrogen and other non-reactive gases. The planet has come full circle. Breathable air, that precious commodity, was merely a brief, billion-year intermission between two anoxic acts. And the microbes won't last forever either. In 2 to 3 billion years, Earth's molten core solidifies further, the geodynamo collapses, and with it, our planet's protective magnetic field winks out. This magnetic field is our shield from the harsh realities of space. Without it, stripped of magnetic protection, the atmosphere slowly erodes under the relentless onslaught of the solar wind. Even nitrogen, once the most abundant gas, drifts away. By 4 billion years from now, Earth's surface will be hotter than present-day Venus, molten in places, a truly infernal landscape. The suffocation that began with the loss of oxygen will ultimately end with a barren, scorched basalt sphere silently orbiting a bloated, red sun, a cosmic cinder where life once flourished. So, next time you take a breath, filling your lungs with that vital air, remember that the oxygen keeping you alive is a limited offer. In roughly 1 billion years, the atmosphere will flip back to an anaerobic mode, suffocating every animal, flower, and fungus on Earth. There won't be a bang, no interstellar explosion, just a slow, quiet leak of the very gas that makes complex life possible. The sun brightens, CO2 crashes, plants starve, oxygen vanishes, and microbes inherit a sauna world. Earth's billion-year countdown to suffocation isn't a distant fantasy, it has already started. The lease on breathable air is renewable only in the cosmic short term. After that, silence.